Hello and welcome to Maths with Jay. So here we're looking at a 2x2 matrix and we want to find its eigenvalues and eigenvectors. So what we're looking for here is position vectors of points which are mapped to scalar multiples of themselves by a linear transformation. So the matrix A represents the linear transformation. X represents a non-zero vector, so the vectors which satisfy this equation are eigenvectors, and the scalar lambda represents an eigenvalue. Well, in fact, in general, we expect to find that we'll get two eigenvectors and two eigenvalues for a 2x2 matrix. So for each eigenvalue, then we'll go on and find the eigenvector, or rather an eigenvector, because we'll find that in fact we can have an infinite number of eigenvectors for each eigenvalue. And then afterwards we'll have a look at how we can look at these invariant lines and see what it actually means to have different values of lambda, what effect that has on the points, on the vectors, on the invariant line. I'm going to start by subtracting the lambda x from both sides here, and because we want to take the x outside a bracket, what we're going to do is put in an I to represent the identity matrix. So whenever we multiply a vector by the identity matrix, it stays where it is. So it's a bit like multiplying by 1 in ordinary arithmetic. And note that because this is a vector equation, I am indicating that x is a vector and that we've got the 0 vector on the right hand side now. So now let's put in some brackets so that we've got a minus lambda I multiplying our vector x, which is a non-zero vector, remember. And because x is non-zero, then that must mean that the determinant of the matrix a minus lambda I must be equal to 0. So the determinant is just a number, so we don't now underline the 0. So we can write this as we've got 5 in our matrix A, and we want to take away lambda times 1, so that's take away lambda, and then the minus 3 will stay as it is, and so will the minus 6 because we're just taking away 0 there, and then 2 minus lambda here. And so that's going to be equal to 0. So working out what that is, we're multiplying the elements of the main diagonal 5 minus lambda and 2 minus lambda, and then subtracting negative 3 times negative 6, so that will be minus 18, so that will be 0. And remember, we're aiming to get a quadratic equation here for our characteristic equation, and we can see that that's going to happen. When we multiply this out, we get lambda squared minus 2 lambda minus 5 lambda, so that's minus 7 lambda. 5 times 2 is 10, and then we can simplify that by combining together the constant terms, so we end up with our characteristic equation, lambda squared minus 7 lambda minus 8 is 0. And we're going to hopefully factorise this to find the values of lambda. So lambda is our eigenvalue, or rather our eigenvalues are represented by the two values that we get for lambda here. But before we go on and factorise this, let's just see another method that we could use here. So the characteristic equation for a 2x2 matrix is actually really simple to write down if you use the trace of the matrix. So let's just write down what the equation would be. So the lambda again is representing our eigenvalue or eigenvalues, and the relevant equation, our characteristic equation, is lambda squared minus the trace of a times lambda plus the determinant of a is equal to 0. And if you're wondering what the trace is, well, it's simply the sum of the elements on the leading diagonal. So in our matrix A, the elements to add together for the trace are just 5 and 2. So in this case, our characteristic equation is simply going to be lambda squared, the trace of A is 5 plus 2, and our determinant is going to be 5 times 2 minus negative 3 times negative 6. And of course we want our equals 0 at the end. So 5 times 2 is 10, minus 18, it will be minus 8. And so we've got exactly the same equation as we had before for our characteristic equation. So let's just put that to one side. So however we've done it, we've got our characteristic equation, lambda squared minus 7 lambda minus 8 is 0. So we're going to factorise that. And we're going to get, well, it must be plus 1 and minus 8 in order to get minus 7 lambda and minus 8. And then that means that we found our eigenvalues. So solving our quadratic equation gives us that the eigenvalues are minus 1 and 8. What you might like to do here is use subscripts, so you might like to say lambda 1 and lambda 2. Right, so we found our eigenvalues, so the next thing to do is to go on and find the eigenvector associated with each eigenvalue. So let's start with lambda equals minus 1. And what we're going to do is we're going to use the equation we looked at earlier on, the a minus lambda I multiplied by the vector x is a 0 vector, and we're going to write that down in matrix formation. So a minus lambda I is 5 minus lambda, the minus 3 and the minus 6 won't change, and then 2 minus lambda. So this is the matrix A, and we're subtracting lambda times the matrix I. And then the vector x can be written as xy, and that's equal to the 0 vector. So we're substituting in lambda is minus 1. So we've got 5 minus negative 1, which will be 6. The minus 3 and the minus 6 not affected by lambda. 2 minus negative 1 is 3. And multiplying xy gives us 0, 0 vector. So the equations we've got here are 6x minus 3y is 0, and negative 6x plus 3y is 0. So in fact those are the same equation, and if we simplify them, 2x minus y is 0, so we can say, well, y is equal to 2x. So all we need to do now is choose a value for x, and the simplest thing to do is to say, well, let's take x is 1, and then y would be 2 times 1. So now we've got an eigenvector, so it's not unique, there are loads of different ones, an infinite number of eigenvectors. So an eigenvector associated with this eigenvalue is, what did we say, x was 1 and y 2. So we've got our eigenvector to go with our eigenvalue. It would be a good idea to check this, wouldn't it? So what we should find is that when we multiply our matrix A by this eigenvector, that we ought to get lambda times this eigenvector. So let's have a look at what happens. So A multiplied by x, well, a is 5 minus 3 minus 6, 2. And our x that we found is 1, 2. So when we multiply this out, 5 times 1 is 5, minus 3 times 2 is minus 6, so that's going to be minus 1. And then minus 6 times 1 is minus 6, so plus 2 times 2 is plus 4, so that's minus 2. So that is in fact equal to minus 1 times 1, 2. And that, remember, is our value of lambda multiplying the eigenvector that we've just found. So that's correct. Our check has shown that this eigenvector and the eigenvalue are correct. So now let's do the same thing with our other eigenvalue. So we're going to be looking at lambda is 8. So let's just move that over to the side. Right, so now we're going to look at the other eigenvalues. So we're looking at lambda is equal to 8. And substituting in, we will get 5 minus 8 is minus 3. And then the minus 3 and the minus 6 as before. And then we've got 2 minus 8 is minus 6. And then we've got our x, y equal to 0. So the equations that we get from that are going to be minus 3x minus 3y is equal to 0. And minus 6x minus 6y is equal to 0. So as before, those two equations are the same as each other, and they can be simplified to x plus y is 0, or if we want to make y the subject, y is negative x. So if we do as we did before and choose x as 1, then y would be minus 1. Again, you can choose any value for x, so there are an infinite number of eigenvectors, but we can say that one of them, so an eigenvector, is 1 minus 1. And of course we want to check that. So checking that, we've got so our vector A, 5 minus 3 minus 6, 2, and we've just found that we think that this is our eigenvector. So let's see what happens when we multiply matrix and vector together. Well, we get 5 times 1, and then we're adding on negative 3 times negative 1, so that's 5 plus 3 is 8. And then negative 6 times 1, that 6 could be a bit clearer, couldn't it? So negative 6 times 1 and 2 times negative 1 gives us negative 8. And then we want to factorise, take out the common factor there, which is of course our eigenvalue, so that's our lambda, and that is multiplying our eigenvector, so that is equal to lambda x. So again, we've got the right answer. So we have got the eigenvalue minus 1 with the eigenvector 1, 2, and the eigenvalue 8 with the eigenvector 1 minus 1. So let's now have a look at how we can visualize those. So I've summarized on this piece of graph paper what we found so far. For the matrix A, we have 2 eigenvalues. So we've got an eigenvalue of minus 1, and its associated eigenvector is 1, 2, and that came from the equation of the line y is 2x. And similarly, an eigenvalue of 8 associated with the eigenvector 1 minus 1 with the equation of the line y equals minus x. So what we'll do here is we'll draw the lines and have a look at what happens to the eigenvectors under the transformation A. So we'll start with y equals 2x. So if y is 2x, we know that it must go through the origin. And when x is 4, y is going to be 2, 4. So that will give us a point up here. And similarly, when x is minus 4, y will be minus 8. So we've got a point down here at minus 4, 8. So let's join them together. So we get this sort of thing happening. And now let's have a look at our eigenvector. So that was 1, 2. And what happens to it under the transformation of A. So that we can see that when we transform this, it ends up going to minus 1, minus 2. So it's ended up the opposite side of the origin to where it started. So let's just have a look at what would happen to minus 3, minus 6. And the same sort of thing happens to that. It again moves to the opposite side of the line. It's the same distance from the origin as it was to start with, but it's on the opposite side. So that fits in with our checking that we did earlier on. Let's now have a look at the other line. So here we've got the line y equals minus x, and we can see what happens to the point 1 minus 1 under the transformation A. It ends up at the point 8 minus 8. So this time it's staying on the same side of the origin as it was before, but it's moving 8 times further away. And we can have a look at what happens to the point minus 1, 1. And the same sort of thing happens. So here it's as if the line is being stretched out under the transformation. Every single point on this line is moving so that it's 8 times further away from the origin than it was to start with. So the only point that remains where it was is the origin. So this is actually a good demonstration that when we say we're asking you for an eigenvector is not unique. An eigenvector could have been 2 minus 2 or negative 3, 3. So it's any multiple of the one that we've written down. So here we can see that these are the two lines that are invariant under the transformation A. And we've seen that that means that there's only one point on each line that stays where it is, but all the other points move within the line itself. For our first eigenvector, where lambda was minus 1, the points swapped sides, and our second one, the points stayed on the same side of the origin, but stretched away from the origin and from each other. So it's important to remember that when we're working with transformations like this, the only points that scale in this way are ones which are on the eigenvectors. So you might like to check this for yourself by having a look at what happens to another point, a point that's not on one of those lines. So for example, what would happen to the point 5, 4?